Our next project comes from one of our remote researchers, Jamie Boyd. They've been working on what they call the macro engineering reader, which is a retelling and restaging of the discourses around what the expanded notion of geoengineering that we've been working with, and astroengineering, and the role of fictive projection within both of these. As you'll see, the argument that is proposed is one that is explicitly critical of the necessity for science fiction, and the ways in which science fiction, as will be discussed, is symptomatic of an inability to integrate the imaginative potential of technologies, economic, engineering, social, political, and so forth, into actually existing infrastructure. It's a kind of deferral, if you like. This is linked with the supposed super agency that is given to within science fiction, in many cases, to the technical capacity of alien civilizations. In essence, this, instead of these stories of omnipotent civilizations capable of the construction of Dyson spheres and so forth, instead of seeing these as less the self-congratulatory fantasy of modernity getting high on its own supply, it's more a symptom of the failure of its capacity of this imagination to directly animate actual science, technology, and politics. The dream is repressed. And the call for it in this way is less an increasing expansion of this imagination on its own terms, but a grounding of it in the circumstances of the real. So the old Marxian adage of the circumstances of make these advanced technologies possible, but also prevent them from reaching their full potential, is a kind of key leverage point here as well. Also, in perhaps versus her notions that these technologies represent a kind of Promethean quest that goes beyond the norm, it's really more a matter of making good on the existing potential that they present to us in this way. One of the other, I think, really important aspects of this project has to do with the way in which Jamie integrates multiple discursive traditions, from science to science fiction, to literature, to philosophy, to humanities more generally, into a kind of integrated story, such that the distinction between these cultures, the differentiation between them, their lack of encounter, is seen as a kind of symptom within a symptom of this disengagement of the fictional from the real. So, as with all of the remote researcher project, this is really a presentation of a longer paper, which we will publish at Stroka in the coming days and weeks. And so, as you go through this, think of this as a kind of introduction to the longer read, which we'll make available soon. So, with that, let me introduce Jamie Boyd and the Macro Engineering Reader.
Hello, my name is James Boyd. I am an Associate Research Fellow at the Terraforming Project at the Strelka Institute. I am also a futurist and a graduate student at the New School in New York City. My project is on the relationship between macro engineering, science fiction, and mathematical formalism, and the possibility of moving beyond literary fantasy towards rigorously designed, advanced architectures at astronomical scales. Thank you. The Macro Engineering Reader by James Boyd. The future begins as a calculation on the back of an envelope. Envelope xi sub n-1. When terraforming Mars, the melting of subsurface ice by an increase in surface temperature is constrained as follows. Tau is equivalent to d squared divided by k. For time tau, subsurface depth d, and thermal diffusivity, K, equal to 2.8 times 10 to the negative 7 meters squared per second. For a nanotube composed space elevator, the expected rate of destabilizing thermodynamic fluctuations is S equals K sub B times the natural logarithm of uppercase N factorial divided by uppercase N minus lowercase n factorial times uppercase N factorial for a structure with N atoms and lowercase n vacancies, where K sub B is Boltzmann's constant. The temperature of an aluminum film for a solar sail is constrained as follows: 1 divided by r squared times a divided by e times p sub theta divided by sigma, where r is the distance of the craft from the sun in astronomical units, a is the absorptivity, e is the emissivity, p sub theta is the solar constant at 1 astronomical unit, and sigma is the Stefan Boltzmann constant. When engineering a Jupiter brain computer from a planet, the memory capacity is constrained as follows: I equals e divided by k sub b times t times the natural logarithm of 2 plus logarithm base 2 of the summation over I of e to the power of capital E sub I divided by k sub b times t. For temperature T and average energy E, given Boltzmann's constant, k sub b. 1. Obsolescing science fiction. Science fiction is a highly ambivalent methodology installed loosely at the extremity of human technological development. It is a placeholder for the institutional capacities of strategic foresight that humankind has failed to develop. A futurist humankind would institutionalize parallel, longitudinal, and interdependent R&D tracks, scheduled across timescales, widely variant in dilation. What we have instead is a marginal, renegade movement within the academy, one that upsets the divide between science and science fiction, threatening both. Science fiction is an informal marketplace in which propositional technologies are sold as pulp and bought because they may not be realized in any other way. At its best, science fiction extends systematic thought beyond synchronic trends in the methodologies of observational science. Science fiction can anticipate and spur technological development. To quote J.G. Ballard, "What the writers of modern science fiction invent today, you and I will do tomorrow." Hugo Gernsback's works foresaw many future communications technologies, and his writings were serialized in popular magazines, such that his advertisements for future technologies sat right beside advertisements for current ones. At its worst, however, science fiction is freelance rent-seeking from unrealized futures and provides an alibi for scientific stagnation. After all, science can always excuse its lethargy by dismissing wanting deliverables as mere science fiction. Nothing endangers this arrangement more than the innocence of feasibility studies for unrealized technologies. 2. The necessity of invention. The comforts afforded by contemporary technological progress cannot guarantee their own permanence. It is not only the case that humankind is imperiled by its own despoliation of the Earth. Over a sufficiently long time span, all fixed planetary habitation is fatal. As our sun exits the main sequence and becomes a red giant, earthly proximity thereto will become dangerous. Other risks include solar superflares, geomagnetic reversals, and gamma-ray bursts. Such realizations spurred a newfound serious interest in advanced off-planet engineering. Envelope psi sub n. When attempting to augment the orbital radius of the Earth via a two-body gravity assist from Jupiter, the impact parameter B sub e and turning angle a sub e are constrained as follows: uppercase B sub e equals lowercase b sub e times the square root of 1 plus mu sub circle plus divided by lowercase b sub e times uppercase v sub e prime squared, and lowercase a sub e equals 2 times the inverse tangent of mu sub circle plus divided by lowercase b sub e times uppercase v sub e prime squared. For gravitation parameter mu sub circle plus, Earth distance lowercase b sub e, and encounter speed uppercase v sub e prime squared. A human designed to hibernate intermittently so as to engage in indefinite spacefaring without hyperthermic costs incurred due to the heat death of the universe, has a finite metabolic rate over infinite time constrained as follows. We integrate from t naught to t infinity m of t dt equals bq, where b equals 6.10 to the 4 ergs, where m expresses energy dissipation as a function of time t, and q is the 10 to the 23-bit complexity of a human being. 3. Macroengineering. Humankind continues to struggle to advance the limits of its own understanding of the emergent effects produced by unintentional anthropogenic design. The limit of scale, reach, and extensivity of intentional anthropogenic design, both minima and maxima, are even less known. However, there exists a field of engineering that admits into its project range everything from the Great Wall of China to galactic architectures on the order of Isaac Asimov's foundation. They call it macroengineering. Macroengineering offers a hint at an institutional practice capable of obsolescing science fiction. But first, macroengineering will have to reconcile its relationship with science fiction. The earliest work to use the term is macroengineering, a capability in search of a methodology, which suggests that large-scale projects are possible if new forecasting and development strategies are created to coordinate decision-making and resource allocation on a large scale. William Jones writes the first analytic work on the topic in a working paper for the MIT Energy Laboratory, which provides both a definition and analysis. Quote, macro, meaning large or extensive, as applied to engineering, can describe size, technical difficulty, time required for design and construction, initial cost in money, size of labor force, time to completion, magnitude of impact, etc. Unquote. Progressively, macroengineering acquired institutional credentials. The author bio in Davidson, 1979 reads, quote, Frank P. Davidson is a lecturer on macroengineering at MIT and chairman of the System Dynamics Steering Committee at the Sloan School of Management, unquote. However, with time, the scale definition of the macro grew, and the resources of science fiction became difficult to decline. But science fiction and institutionalization were not reconciled, and the passive, fanciful variety of science fiction has prevailed. Such is apparent in the meretricious character of contemporary macroengineering, wide in project spectrum and devoid of an overarching methodology by which pathways might be articulated. For instance, decades later, Davidson edits a volume on the topic, which includes essays on financing large-scale projects and a study on the construction of Abuja, Nigeria. However, if one keeps reading, one sees essays on automation for space missions and orbital architectures. Take two other key figures in the field, Badescu and Cathart. We can find works by the two on terrestrial projects. Badescu and Cathart edit a volume on macroengineering with application to maritime transport, water body treatment, and hydrological civil engineering. The volume includes essays on the engineering of the World Islands and Palm Islands in Dubai, the proposal of aquifer and canal project solutions for the restoration of the Dead Sea, habitat engineering in the Strait of Hormuz, dike architecture proposals for resisting coastal hurricanes in the Gulf of Mexico, and proposals for large-scale desalination plants. In another volume edited by Badescu and Cathart, the fuller breadth of macroengineering is shown, with works ranging from geoengineering, carbon capture, and solar power technology, to space towers, artificial gravity, stellar engines, and galactic-scale civilizations. Here, the macroengineering extends from megascale engineering and geoengineering on Earth to another field known as astroengineering. Although there are astroengineering studies about human engineering on astronomical scales, the majority of astroengineering suffers from the worst aspects of both science fiction and observational science and has little to do with engineering. 4. The perniciousness of astrobiology. Astroengineering architectures include artificial planets, shell worlds, the radical modification of planetary geometry, solar or galactic scale artificial habitats, Dyson spheres, which are solar scale architectures for stellar energy capture, Jupiter brains, planets engineered to become computers, and advanced spacefaring technologies such as Alcubierre drives and Krasnikov tubes. To be clear, however, astroengineering originates in the works of science fiction writers such as Olaf Stapleton, whose work, Star Maker, would come to influence Freeman Dyson's work on Dyson spheres, early transhumanists such as J.B.S. Haldane, and Russian cosmists. However, beginning in the 1960s, such works began to be taken up by astrobiologists. The impetus was the development of the Kardashev scale by Nikolai Kardashev. Kardashev presents a typological classification scheme for stages of civilizational advancement according to energy use: planetary scale energy command at type 1, solar scale energy command at type 2, and galactic scale energy command at type 3. Contemporaneously to Kardashev, Dyson develops theories on the kinds of technologies that advanced civilizations might use, referring back to Star Maker. Dyson and Kardashev would work together, and Kardashev would become interested in studying astroengineered artifacts as manifestations of advanced civilizations. The practice of conducting astrobiological observation for astroengineered artifacts and manifestations rather than electromagnetic signals is referred to as Dysonian SETI. SETI researchers interested in astroengineering often search for Type 2 civilizations, Type 3 civilizations, and even Type 4 civilizations. The majority of astroengineering studies, including Cherkovich's paper on galactic scale structures in the Badescu and Cathcart volume, are of an observational astrobiological character. Running contrary to the thrust of science fiction, astroengineering studies constitute a hopeless observational science. Rather than grapple with the aspirational challenges of human astroengineering designs, astrobiologists have delegated the job to hypothetical, anthropomorphic intelligent species. In so doing, they have forsworn the greatest resource offered by science fiction, the investigation of the limits of anthropogenic design, as well as the limits of human understanding, which should caution us against presuming that extraterrestrial intelligence would be anything like human intelligence. Envelope xi sub n plus k. In the deep future, the computational efficiency afforded by cosmological thermodynamic entropy is constrained as follows. E is greater than or equal to k sub b times t times the natural logarithm of 2 joules for energy E, temperature T, and Boltzmann's constant, k sub b. The change in velocity, delta v, for a Buzzard ramjet designed for interstellar spacecraft exploiting relativistic travel is constrained as follows. Delta v equals the hyperbolic tangent of I sub sp divided by c times the natural logarithm of m naught divided by m sub 1, where c is the speed of light. I sub sp divided by c equals the square root of 2 eta minus eta squared is the energy yield for eta fuel. M naught is the ex ante spacecraft mass, and m sub 1 is the ex post mass. 5. Towards institutionalization. Certain practitioners within engineering have motioned towards the development of methodologies capable of both satisfying the role of science fiction and introducing methodological rigor amenable to institutional regularization. The most promising is exploratory engineering, the technique of deriving constraints and affordances for conceptual technologies from first principles towards the demarcation of R&D pathways. It is a powerful gesture to progressively chip away impossibilities until the bounded region of feasibilities become demarcated. I care not about your love letters to the stars. I throw away the letter and look at the scratchings on the back of the envelope.